The topic of this problem is maximum power, and we're working with circuits with dependent sources. The problem is to find the Thevenin's equivalent circuit and to use it to determine the load resistance for maximum power and the value of the maximum power delivered to the load. So here's our initial circuit from our previous video problem. So this was the circuit that we started with for our previous problem. And then what we did was we worked through this problem finding VOC, finding I short circuit, so that we could ultimately write the circuit in the form of a Thevenin's equivalent circuit, which contains the VOC, R Thevenin's, where R Thevenin's is equal to VOC divided by I short circuit, and the load resistance. So our initial circuit has everything we need, and we're going to determine what R sub L is for maximum power delivered to R sub L. And then we're going to determine the power associated with R sub L. So we know through the maximum power theorem that maximum power is delivered to a load when R sub L is equal to R Thevenin's. We found in this problem from the previous video solution to it that R Thevenin's is equal to 8 kiloohms. It's VOC, which is 8 volts, divided by I short circuit, which was 4 milliamps. And so that ended up giving us 2 kiloohms for R Thevenin's. If we want for maximum power delivered to our load, the condition that R sub L is equal to R Thevenin's, then our R sub L in this problem is going to be equal to 2 kiloohms. That's our value for R sub L. Now, if we know that and we want to find the maximum power delivered to that R sub L, then we can use our simple equation for power, which relates the power to the voltage. So we have V R sub L divided by V squared divided by R sub L. And we know what the voltage is going to be across R sub L using voltage division of our simplified Thevenin's equivalent circuit. We have an 8 volt source. We have a 8 kiloohm resistor. We now have identified our load resistance as 8 kiloohms. So our voltage drop across this is going to be the voltage division of the 8 volt source between these two resistors, which are the same. So VRL is going to be 8 volts, and then R sub L, which is 8K, divided by 8K plus 8K. That's the amount of the 8 volt source, which is across the load resistance of 8 kiloohms. And we know that number is in fact going to be 4. So we have a 4 squared at the top, and we have a load resistance which is equal to 2 kiloohms. So the power in this case is going to be four squared, which is 16 volts squared, divided by 2 kiloohms. So that gives us 8 milliwatts for the power. And that's a power max delivered to the load.